In this video, we'll see how to actually use equilibrium constants. And the first thing we'll probably want to do is figure out how to get it in the first place. And so, if we take for a reaction, let's use our favorite reaction, the Haber process, the one making the ammonia. All of these are gases, as we know. Let's say the equilibrium value, the first way that we can get an equilibrium constant is experimental. Once the system reaches equilibrium, we can measure all of the concentrations of our reactants and products, and we can figure it out based from there. So let's say the pressures, we'll figure out, we'll do Kp first. At equilibrium, were found to be, we'll say, how about 3 atmospheres of hydrogen? Again, I'm just making up these numbers. So the Kc is a constant at a particular temperature. So don't be looking these up and be like, aha, you've got the wrong number. Again, these are just made up problems. 0.621 atmosphere of nitrogen, and let's say 1.422 atmospheres ammonia at 80 degrees Celsius. We don't really need the temperature here. It's just to indicate that. Remember that rate or equilibrium constants are dependent on temperature. So because rate constants were dependent on temperature. So once we have our temperature established, we're assuming that temperature is not changing, and so we can do this. So if we're to find Kp for this, we could say, aha, well, we know that our equilibrium expression is our products raised to their power over the reactants raised to their powers. And since we have the equilibrium pressures already, I'm sorry, did I put concentration for all these? Shame on me. These are pressures. We can simply plug in the values. So 1.422 squared. Our hydrogen is 3 cubed, and then we have 0.621. Thankfully, by the way, for equilibrium constant, we typically don't include units. For example, the units here would be atmospheres to the -2 power if we were to plug in the units after doing the calculation. It's not really a sensical unit, we kind of just ignore them. So that's pretty standard practice. So thankfully, that saves us a bit of thinking, right? As long as everything's the same unit, we're okay. So let's calculate. So 1.422 squared divided by 3 cubed. Oops. 1.422 squared divided by 3 cubed divided by 0.621. Oh goodness, hold on, my calculator messed it up. 1.422 squared divided by 3 cubed, divide that by 0.621. There we go. And so for this, I've calculated Kp to equal 0.12 3 sig figs, so 1. And again, we're not going to include units. If you really want to, go right ahead, but it's very strange to do that, so we typically don't do it. So that's how we can calculate the equilibrium constant. And as we saw before, because we didn't necessarily do a problem with it, we can go ahead and calculate Kc as well. If you remember, we can relate Kp to Kc with the following expression, right? We saw that it's related to the RT to the delta N power. And so, in this case, we have Kp, 0.121, equals Kc times 0.808206, 0.8206, sorry. And then we have our temperature, which is 80 Celsius. Let me quickly convert that to Kelvin, 273. We have 353 Kelvin. And we're going to need to raise that to the -2 power, right? Because we saw for this reaction, We have 2 moles of gaseous products, 4 moles of gaseous reactant. I've added the coefficients together. So that's a -2 power. And so Kc, if we just plug stuff in and solve for it, we can do that. 0.08206 times 353 raised to the -2 power. And then we have 0.121 divided by that number. Kc is going to be 101 or actually I guess 102. Again, we don't need to worry about units here. In this case, now we've calculated our Kc. So all we did was plug it into the equation. Remember that delta N, that's the only tricky part. That's moles of gaseous products minus moles of gaseous reactants. And so now that we have that, we have our Kc, we have our Kp, we can use them for whatever we might need. And in our next video, we'll actually see how to use these values in calculating the equilibrium concentration.